All right, today we're going to look at the first half of area under a curve and how that applies to Riemann sums, which is a very big topic in calculus in the sense of estimating the area under a curve. So we just finished talking about integrals, indefinite integrals, and U substitution, and we will come back to that again at the end of this unit. So far, however, right now, we just have it as this basic concept or this basic idea that integrals and derivatives are opposites of each other. And we haven't really made the connection to what that means yet in terms of like the application of an integral. So we know that the application of a derivative is the slope of the tangent line in the sense of estimating how quickly things are changing using average rate of change, and then in calculus being able to figure out exactly how fast things are changing using derivatives because we can figure out the instantaneous rate of change. And so that's how derivatives become applicable to the real world and to real life problems. And in second semester, now talking about integrals, we will start to talk about how these are applicable to real life problems and what they help us to figure out. So far all we've done in this unit is do some algebraic integrals and figuring out how to find integrals. And now we're going to go into kind of a little bit more of an application-based process and figuring out where they apply. And then, like I said, at the end of the unit, we'll come back to talking about algebraic integrals again and how figuring out integrals algebraically helps us to solve problems. So, area under a curve is where we're going to start this whole concept-based part of the unit. So, for example, up until this point in your lives, you've only ever been able to calculate area of things that have straight lines typically, or things you have formulas for. What I have pictured here is an equation. Who knows, maybe it kind of looks like a cubic equation possibly. And so our job is to estimate the area of this equation. And so if I let you do it, you'd probably sit here and think about it for a little bit, and you might have different strategies for how you would do it. And because we're not here in front of each other, I can't ask you what all of your strategies are, but just to give you a heads up of some of the ones I've heard before. Some people would like to divide it into shapes that they do know how to find the area of. So like, for example, I've seen people say that they could find the area by looking at this as like a rectangle, and then possibly looking at it as possibly even like a larger rectangle, going all the way over here. And then I've seen people do like a triangle to estimate that area, and then maybe another rectangle and another triangle or something. I've seen people do that before, and they get a pretty good estimation of what the area should be that way. Another way I've seen it done before is some like people counting up every single little individual box. So they'll like count up all of these little boxes. And then the ones that are partial boxes, like you guys can see here that this is a partial box. The ones that are partial boxes, they'd like estimate and try and put together the pieces of the area that way. And then eventually we kind of lead into this whole idea of using one shape. Because if we can use one shape, then we can start to make patterns out of it. And that's what we're going to get into with Riemann sums, is with Riemann sums we use rectangles. And we don't always use rectangles of different lengths, or different, widths, I should say. So in that first picture I drew, you could see we used a couple of different rectangles and triangles, but I don't really want to fit them to fit into the pattern. I want to show how they work on top of the pattern. And so let me show you what I mean. Let's say we used two rectangles to estimate this area. So here's a rectangle. And that one actually fits pretty close. It's a little bit more than what the area should be of that piece. But on this other side, it's hard to use one rectangle to kind of figure out what the area should be. So like, if I draw the rectangle up here, I hope it's pretty obvious that that's like a gross overestimation. If I draw the rectangle down here, it's pretty obvious that's a gross underestimation. I could draw the rectangle somewhere in the middle, and you have a little bit that's over and a little bit that's under, but you don't know exactly like which one's more or less and if this is approximate or not. So then we go to like, what if we use four rectangles? All right, that one's pretty close, that one's pretty close, that one's a little bit over, and that one's a little bit over, but probably not as bad as it was in the previous section, because remember in the previous section we had all this extra rectangle as well that was also over. And then we go to talk about what if we use 8 rectangles. So here's me drawing 8 rectangles. And again, the way that I've drawn it, you can see that it's a little bit more than it needs to be, but much less than it was even before. And so you can see the more and more rectangles I draw, the closer and closer that this is going to get to a pretty good approximation of what the area will actually be under this curve. And this is what we're going to be doing with Riemann sums. The rectangles I've drawn are called right-hand rectangles because notice that I always drew them from the right-hand side. So like this rectangle I drew from the height of the function, I drew out to the right and then down. From here, I drew it from the height of the function out to the right and down. From here to the right, down. I can also do left rectangles. So if I go from the height of the function to the left, like this, you can kind of see that these rectangles are underneath the curve because I went from the left-hand side. So all these left endpoints, and I drew them out from the left part of the function and then drew a rectangle that went down like that. So depending on whether or not your original function is increasing or decreasing, and then depending on whether or not you're drawing left-hand rectangles or right-hand rectangles, will decide whether or not your approximation of the area is going to be an overestimation or an underestimation. So as you can see in what I have drawn here, this is an underestimation because it's below the curve, and so I don't have enough area. There's pieces that I'm missing. Versus the one I had drawn originally, it was above the curve, and so I had too much area. So that was an overestimation, whereas this is an underestimation. So, like I said, we could go through this process over and over again, getting more and more accurate by drawing more and more rectangles. And the more rectangles you create, the more work you have to do, which is kind of where we get into the whole downside of doing that. But it gets more and more accurate when you make more and more rectangles. Now, this is the formula for the true area, like the exact area. So I just want you to look at it really quick, and I'll kind of walk us through it. So a couple things you need to know. N is the number of rectangles. So look at this as the limit as n approaches infinity, meaning that we're getting to an infinite number of rectangles. We start at I equals 1 and go to n, the number of rectangles. And A is the area of each rectangle. So essentially this means you start at rectangle 1, and then I don't know if you guys recognize this symbol. This is the Greek letter for sigma, and in math, the Greek letter for sigma means summation. So this is a summation symbol, and essentially it means to add together every single one of the areas. So the true area is if we had an infinite number of rectangles, and we could calculate the area of every single one, and we added together all of those areas of all those rectangles, that would be the exact area under the curve. Now, I'm not going to make you actually calculate, excuse me, I'm not going to make you actually calculate the area of 1,000 rectangles and add them all together. That would be impossible to do, or an infinite number, I should say, would be impossible to do. 1,000 would just be tedious and annoying. So when we do Riemann sums, they give us a more manageable number of rectangles, which obviously means our answer is not going to be as accurate, but it will be a good estimation of what it would be. So here's an example down below. It says, find the area of the following function using the indicated number of rectangles. And we said f of x equals x squared plus 3 on the interval from 2 to 5. So you don't need to draw a picture necessarily, but I will draw us one just so you guys can get a good idea, of what this looks like. So x squared plus 3 is the quadratic function, shifted up 3. And it looks like that. On the interval from 2 to 5, here's 2, here's 5. If I plug numbers into those functions, 5 is a little far away. If I plug numbers into those functions at 2, 2 squared is 4, 4 plus 3 is 7. If I plug in 5, 5 squared is 25, 25 plus 3 is 28. So you can see that those are the 2 points on the graph, and they would essentially want us to create rectangles in here and estimate what the area is by calculating the rectangles like this. So there's an example for part A. I've drawn 3 rectangles inside of that area from 2 to 5. Notice that it's an underestimation. This is a left-hand summation because I came from the left every single time. Now, if you look at the bases, that's one of our jobs, is to figure out how wide the base is. From 2 to 5, if I've drawn 3 rectangles, I hope it's obvious that if I count by ones, this would be 2, the next one would be 3, this would be 4, and this would be 5. So each one has a base of 1, and then the heights are what change. So my height at 2 is 7, we already discussed that. What about at 3? If I plug 3 into the function, 3 squared is 9, 9 plus 3 is 12, so at 3 I have a height of 12. And for this last rectangle, if I plug in 4 to the function, 4 squared is 16, 16 plus 3 is 19, so I have a height of 19. So if I wanted to find the area of each of these rectangles, they all have a base of 1 and they have varying heights. So this first rectangle has a base of 1 and a height of 7, therefore the area is 1 times 7, or just 7. So for part A, it would be 7, plus the area of the second rectangle. It has a base of 1 and a height of 12, so that would be 12. The third rectangle has a base of 1 and a height of 19, so that would be 19. And then if you add all these together, and you're going to need a calculator for this section, you'll see we get to some more intense numbers later on. 7 plus 12 plus 19 is equal to 38. So my estimation of the area under the curve is 38, using left-hand rectangles that are an underestimation. So in reality, the actual area is more than that, but that's my estimation using 3. Now, I don't want to spend our time right now doing part B with 6 rectangles, but you can imagine that if I just drew another 3 in here, I'd have to divide these in half. So right now, each one has a base of 1. If I drew it with 6 rectangles, I'd have to divide each of these in half. So each of these would have a base of 1/2. And then the heights would change. So instead of going from 2, 7, maybe that was my first rectangle, the next one would go from 2.5, whatever the height is at 2.5. The next one would go from 3, and then 3.5, and then 4, and 4.5. And so you get a little bit more of an accurate depiction of what the actual area is under the curve. So this leads us into our discussion on Riemann sums and putting down some formulas on paper and doing some more concrete examples with specifics. In that last example, I kind of chose that I wanted to do left-hand sums. But in this case, we will have specific direction on what kind of Riemann sums to look at. Now, there are 4 types of Riemann sums in total. And we're going to explore that right now. We're only going to look at 2 of them today, and then we'll look at 2 of them tomorrow. But here are the 4. So here, excuse me, sorry, that's my dog. Here is an example of a function we could be working with, and this black area over here is the exact area under the curve. So you guys can see that it fits perfectly. Obviously, there are no boxy shapes, so this is not the Riemann sum version. This is the exact area under the curve. And it's going from 1 to 5, x equals 1 to x equals 5. So we're going to look at these 4 techniques, right rectangles and left rectangles. We're going to look at those today. Midpoint rectangles and trapezoidal rectangles. Oh my gosh, trapezoids, not rectangles, just trapezoids. We're going to look at those 2 tomorrow. So we have 4 different ways that we can estimate the area under the curve. The most accurate ones are typically midpoint and trapezoids. I think trapezoids are typically the most accurate, and then midpoint's not far behind. Left and right rectangles are not very accurate, but they do help us with finding like a very maximum and a very minimum. So here's a picture of all of them. Excuse me. Right rectangles. You can see they come from the right-hand side, so let me put a little star so you can see this. Notice that rectangle touches, the right-hand side of that rectangle touches the function. The right-hand side of this one touches, the right-hand side of this one touches, the right-hand side of this one touches. So that's why we call them right rectangles. So from the intervals that you have decided at the bottom, remember we said this was from 1 to 5. So this is 1, 2, 3, 4, 5. So for a right rectangle, if I divide up my intervals into the appropriate number of rectangles, I would look at all the right-hand numbers. So I would start at 5 and figure out what's the height at 5, then what's the height at 4, then what's the height at 3, what's the height at 2. Notice that we don't care about the height at 1 because we don't even touch the height, or the function, I should say, at 1. Then left rectangles. We go from the left-hand side. So you can see we care about the height at 1, 2, 3, and 4, and we actually don't care about the height at 5. So at 1, it's touching the function. At 2, it's touching the function and going from the left. At 3, it touches and goes from the left. At 4, it touches and goes from the left. And notice at 5, we don't actually have a rectangle that's at that height. Midpoint would go from the middle of the interval. So notice that it touches at the middle of every rectangle. So this one's pretty accurate because a little bit of the rectangles are going to be an overestimation, and a little bit of each rectangle is going to be an underestimation. So that helps us to approximate a little bit better as well. And last but not least, trapezoids. Notice that the tops of them are slanted. They're not actually horizontal lines to create rectangles. They create trapezoids that are on their sides. And so we just kind of connect the left and right hand points together to form this trapezoid and find the area that way. But like I said, that'll be for tomorrow's lesson. And then just a few more notes before we do an example. One of the commonly asked questions on the AP test is looking at left and right Riemann sums, which of them are over approximations and which of them are under approximations. So notice that it depends on whether or not you're looking from the left or right, and then also it depends on whether or not your function is increasing or decreasing. So these first two are examples of decreasing functions. Notice that if my function is decreasing, if it's going down, and I take my rectangles from the left, that they're going to be on top of the function. That's an over approximation. Alternatively, if my function is decreasing and I take my rectangles from the right-hand side, notice that they're all underneath the curve. That's an under approximation. And then it changes when you are increasing. So if we have an increasing function from the left, it's an under approximation, and an increasing function from the right is an over approximation. Now, this isn't something I want you to memorize necessarily. It's just something I want you to understand. If it meant that you had to draw out this picture every single time to figure out, like, is my function increasing or decreasing? Am I coming from the left or the right? And then kind of physically drawing in the rectangles to see if it's an over or under approximation, then that's fine. I don't want you guys to try to memorize this because memorization never really works. All right, so here's an example of a previously released AP test question. It says the graph of function f is shown above on the interval from 0 to 3 of the following, which has the least value or the smallest value. So we haven't learned this notation quite yet. So you guys aren't probably 100% familiar with this, but I'll kind of lead you towards what it's talking about. This is an integral. We have learned about that, but you haven't learned about it when you have these numbers on it yet, and so we'll talk about that closer to the end of this unit. But essentially what it is an integral represents the area under the curve. And so this is saying what is the exact area under the curve. So if I highlighted it, excuse me, oops. If I highlighted this area or colored in this area from 1 to 3, this will be the exact area under the curve. Part B says a left Riemann sum approximation. So with 4 subintervals. So 4 subintervals from the left would be coming from the left, from the left, from the left, from the left. So notice that these are all above the curve. It's all an over approximation. So this I don't think would be the least value because part A was the exact area, which was not an over approximation. So that one was definitely smaller than B. So obviously this one's an over approximation. That's probably not going to be the smallest value. The next one says a right Riemann sum. So coming from the right, from the right, from the right, from the right. Notice that this one is all underneath the curve. And it's pretty significantly underneath the curve. You guys can see there's a bunch of empty blank space missing. So this is a pretty small estimation. So keep this one in the back of your head in terms of it being the least value. The midpoint sum. Remember, the midpoint sum goes from the middle of all these intervals. So if I'm looking at these rectangles, the middle would be here. Now remember that midpoint sums are a little bit over and a little bit under. So those ones are actually pretty accurate to what the actual area under the curve is. So I still think that right Riemann sums are smaller than this because there was more space underneath the curve and less above. And last but not least, our trapezoidal sum. If I connected all these up here to make trapezoids, that's a pretty accurate estimation of what the area under the curve is equal to. So I, again, don't think that that one's the smallest one. So in this example, the smallest value or the smallest area under the curve came from doing the right Riemann sum with 4 subintervals, because you could see that there was no part of the rectangles that were above the curve. It was all below the curve, and it was pretty significantly below the curve. So because this is a decreasing function and we used right rectangles, it was an under approximation, and it was a smaller approximation than all the other options up here. All right, and then this one. It says, if a trapezoidal sum over approximates and a right Riemann sum under approximates, which of the following could be the graph of y equals f of x? Now, the easier one to figure out is the right Riemann sum. We just talked about on the previous couple slides that if it's a right Riemann sum of a decreasing function, it will be an under approximation. So if I want my right Riemann sum to be an under approximation, I need to look at one of these functions that's decreasing. So hopefully you're able to eliminate some of them based on the fact that they're not decreasing. The only two that are decreasing are A and C. So notice that B is increasing, D is increasing, and E is increasing. So those three would not be under approximations for right Riemann sums. Oops. So not that one, and not this one. So I'll just show you one more time. If I draw my little rectangles from the right, notice that they're all underneath the curve. So decreasing functions will always have right Riemann sums that are under approximations because they're all below the curve. Okay? Now, the next piece to figure out if it's A or C comes from the trapezoidal approximation being an over approximation. And it's a little bit hard to tell on a small picture, so I'll try to draw it really carefully. But trapezoidal sums being over versus under approximations actually come from the concavity of the function. So if you look at this function, I'm going to connect from 0 to 4, or sorry, from 0 to 1, and then 1 to 2, and then 2 to 3, and then 3 to 4. I'm going to connect them with straight lines so you guys can see these trapezoids. And then for C as well. All right, there we go. Now, it's a little bit hard to tell, especially in that second picture. In the first picture, it's a little bit more obvious, and also my picture's not the prettiest. But I hope it's obvious that when a function is concave down, when you connect one point from the left and one point from the right, that line's going to be over the top of the curve. And that's true. It's most obvious here between 0 and 1. It's a little bit less obvious here because it gets closer between 1 and 2, and then 2 and 3, and 3 and 4. But you can tell if you look closely that all of these lines are above the curve, which means that this one is over approximating. Versus here, and this one's pretty hard to tell. Excuse me. If your concavity is down, each of these lines is below the curve, very, very slightly below. And like I said, it's not perfect in the way that it's drawn. I wish I could get a little bit closer, and maybe I can get more accurate. If you're connecting them very carefully, you can kind of see that they lie below the curve. Even though it's very, very, very slight, they do in fact lie below the curve. And so this is an under approximation. So like I said, it has to do with the concavity. So maybe we can write that down kind of like how we wrote down those charts last time. If we have a function that's concave up, like this, a trapezoidal sum, trapezoidal Riemann sum, will over approximate. Versus if we have a function that's concave down, like this one was, a trapezoidal sum will under-approximate. All right, so final answer, because we wanted the right Riemann sum to under-approximate and the trapezoidal sum to over-approximate, then our final answer was answer choice A. All right, next. Excuse me. All right, so here's some of the formulas you might want to write down. And I think mostly we go off of concepts rather than formulas, but that's okay. We'll get used to it. It says if we divide our picture into 4 rectangles, we have to find the base of each rectangle. Ideally, all of our bases are the same length. That won't always happen, but ideally they are all the same length. The only time it doesn't really happen is when we're working with tables. But when we're working with equations and things like that, it will. So, we will define our base to be these different values. So, for example, from x equals 1 to x equals 4, if there are 4 rectangles, you would divide that up into intervals of 1 unit each. So, for example, if I can draw it out like this, if we have from 1 to 5, we would count by ones. 1, 2, 3, 4, 5. And notice that I've broken it up into 4 different bases. So from 1 to 2, from 2 to 3, from 3 to 4, and from 4 to 5. Those are 4 different bases. And we call them x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4 to list out all these different numbers. And that will help us to decide which ones we use for which rectangles and which ones we don't use for which rectangles. So for left rectangles, notice that we use all of the ones on the left. So we use x sub 0, which was 1, x sub 1, which was 2, x sub 2, which was 3, and x sub 3, which is 4. On the right-hand side, however, we use the ones coming from the right. So we use the last one, x sub 4, which was 5. We use x sub 3, which was 4, x sub 2, which is 3, and x sub 1, which is 2. So for right rectangles, we ignore the first one, and for left rectangles, we ignore the last one. Now, let's make sure you understand what these formulas are telling us. It says the area is equal to the base. B is the base. So in this case, because they're all 1 unit apart, the base would be 1. And then f of x sub 0, that's the function's value, or the height of the rectangle at x sub 0. This is the height of the rectangle at x sub 1, the height at x sub 2. The reason we can add together all of the heights and then multiply by the base is because they all have the same base. So we can write it like this. If they didn't have the same base, we would have to multiply each area individually and then add them together. And then in this specific case, again, like I said, with the examples that are up here at the top, plugging in 1, 2, 3, 4, and then here plugging in 2, 3, 4, 5. So ignore the 1 because it's the one on the left, and here we're ignoring 5 since it's the one on the right. And these are called Riemann sums. So let me show you an example one more time before we get into our first example. Excuse me. So I just wanted to show you this example. You can see that the green part of the function is above the curve and that the red, above the x-axis, and that the red part of the function down here is below the x-axis. So we're going to start getting into positive and negative areas. So these green values are positive because they're all above the x-axis, and these red values are negative because they're all below the x-axis. Now I just wanted to show you the number of rectangles and how that affects what the estimation would be. So for example, right here you can see some of these rectangles are under-approximating because there's area that's underneath the curve that's left out. And then some of these rectangles are over-approximating because there's area on top of the curve that we don't need. And same thing on the red, and it depends on whether or not it's increasing or decreasing. So these are all left-hand rectangles. Here's what it looks like if it's a right-hand rectangle. You can kind of see that all these rectangles come from the right. And then midpoint, all these ones come from the middle. So you can see that each one has a little bit above and a little bit below. And then the number of rectangles, I can make it less. If I make the number of rectangles less, you can see that the estimations become less accurate because the space below or above the curve is a lot bigger. So here's 1, here's 3, here's 7, etc. And then I can drag it more and more. And then more rectangles I create, you can see that the estimation of the area is getting closer and closer and closer and closer to what it should accurately be. Notice that by the time I get to like 262, you can barely even tell that these are rectangles anymore. Now you can just kind of see that these little dotted things, that it's super, super close to the accurate answer of what the area under the curve is. And the more rectangles I drag, the closer and closer it gets. So notice this is 500 rectangles. You can see that it's a pretty accurate estimation of the area under the curve versus using, for example, only 10 rectangles or 12 rectangles. So the exact area under the curve is the integral. That's the application of the integral. So kind of like what we did in the first couple sections, we're going to come back to that and talk about how that applies to this. But for right now, when we're talking about Riemann sums, we'll do it with a smaller number of rectangles so that we don't get overwhelmed, because it would be a lot to do it with 500 rectangles. All right, so here's our first example. And make sure you write this down in your notes. It says, approximate the area under the graph of the function shown to the right from x equals -2 to x equals 3 using the right endpoints of 5 subintervals of equal length. So from -2, which is right here, to +3, which is right here, and we want 5 subintervals. Notice that if I divide them nice and evenly, from -2 to -1, from -1 to 0, from 0 to 1, 1 to 2, and 2 to 3, there's 5. So here's my first rectangle, my second rectangle, my third rectangle, my fourth, and my fifth. So there's 5 rectangles of equal length we've divided out from -2 to 3. So first thing it says is to use the right endpoints. So remember, if we're using all the right endpoints, we come from the right. To make sure I don't make an error when I do this, I usually draw my rectangle from the right first, and that way I know that once I've hit 5, I'm done. So I come up all the way from 3 until I hit here, and then cross over and go down. Then come up from the right, hit here, cross over, go down. Come up from the right, hit, cross over, go down. From the right, come up, hit, cross over, go down. And from the right, cross over, go down. Now notice that I only used my right endpoints. I used the height at 3, the height at 2, the height at 1, the height at 0, the height at -1, and I did not use the first one. That's for left rectangles. So if we're going to estimate these heights, this first one looks like it's about equal to, I don't know, what does that look like to you guys? 1.75? The second one looks like it's about equal to 2. The third one is close enough to about 2.5. The next one's about at 3. And the last one's at about 2.5 again. I know it's not perfect, but close enough. All right. So what I'm going to do is I'm going to find the area of each rectangle. So each one has a base of 1, because we were counting by 1. -2 to -1, -1 to 0, 0 to 1. And we are going to find the area. So there's 2 ways you can do it. If you're going to use the formula, we would say the area is equal to the base, which is 1, times all the heights added together. So 2.5 plus 3 plus 2.5 plus 2 plus 1.75. And again, please feel free to use a calculator for this. I don't necessarily need you to do it by hand. So 2.5 plus 3 plus 2.5 plus 2 plus 1.75 times 1 is 11.75. units. All right, and then for part B, I got to come back here and erase these rectangles and do them again, but coming up from the left-hand side. So from the left-hand side at -2, that's a height of 0. Then we have this one. From the left, from the left, from the left, from the left, and there's our 5 rectangles. Notice the first one is a height of 0. This one has a height of about 2.5. This one has a height of 3, about 2.5. And this one has a height of about 2. So for my left-hand rectangles, I would say the area is equal to the base, which is 1, times 0 plus 2.5, plus 3 plus 2.5, plus 2. And if I add all those together, I have 2.5 plus 3 plus 2.5 plus 2 times 1, and I got 10. So the area is equal to 10 units squared. All right, so that's how you find left rectangles and right rectangles. And again, as long as the area of the bases are the same, they're all of length 1, then we can multiply by the area, we can multiply by the length of the base at the end. Versus if they were all different, I would have to calculate these areas individually and then add them together. All right, this one, I think we might skip for right now. On the last one, we were doing it from a graph. On this one, doing it from an actual function, you just have to plug in the values. So it's the exact same problem in the sense of doing right and left rectangles, where you would just plug in, like, if we have 4 rectangles, it would be rectangle at 1, at 2, at 3, at 4, and at 5. And you would just plug them into this function to figure out the heights. But like I said, we're not going to do that one right now. So this will be the last one that we do today. It says, a car comes to a stop 5 seconds after the driver slams on the brakes. While the brakes are on, the following velocities are recorded. Estimate the total distance that it took the car to stop. So notice that integrals take us back up. So if we have a velocity function that's being given to us, if we estimate the area under the curve, it will tell us about how far the car went in that time. So, excuse me, we're going to use 5 left and right endpoint rectangles. Notice the bases are all the same, from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. They all have a length of 1. So if I'm going to calculate the area under the curve, for right rectangles, actually it says to do left first. For left rectangles, we would have the area equaling 1, which is the length of each of these rectangles. From 0 to 1 has a base of 1. From 1 to 2 has a base of 2. From 2 to 3, 1 to 2 has a base of 1. 2 to 3 has a base of 1, etc., etc. It's always a base of 1. Now, if you wanted to, you could actually plot these points on the graph and show the rectangles. But I hope it's possible for you to imagine what they would look like, where you have 88 and then 60 and then 40 as your different heights for these rectangles. So for the first rectangle, because we're coming from the left, remember we're going to use all the left points and none of the right ones. So my rectangle here has a base of 1 with a height of 88. The next rectangle from 1 to 2 has a base of 1 with a height of 60. The next rectangle has a base of 1 from 2 to 3 with a height of 40. The next rectangle from 3 to 4 has a base of 1 with a height of 25. And last but not least, my last rectangle from 4 to 5 has a base of 1 with a height of 10. And if I add all these together, I get 88 plus 60 plus 40 plus 25 plus 10 times 1 to be 223. 223, and then the units would be feet. That's the approximation of how far the car went in that time. And then for right rectangles, they all have a base of 1, but this time, instead of going from the left, we're going to go from the right. So we would use 0, 10, 25, 40, and 60. We would not use 88. So it would be 1 times 60 plus 40 plus 25 plus 10 plus 0. If I add all those together, I get 60 plus 40 plus 25 plus 10 plus 0, excuse me, times 1, 135. So the left rectangles are an over approximation. The right rectangles are an under approximation. And so the actual driver's distance to stop was probably somewhere in between those two. but these are our estimations using left and right endpoint rectangles. Sorry that was kind of a longer video. Those concepts I really wanted to flesh out. Tomorrow we will talk about the midpoint and trapezoidal Riemann sums.